so things are, I've been working on issues related with culture for many years, many more than I want to remember. But things are happening now that haven't been happening for a long time. Right? You see it this morning, there's finally data, okay? Now, not that there wasn't data, but you know, not even close at the level that there is now. And you know, so the point now is there's very interesting data, mostly unexplored, not much explored because it's new. There are models, most of them not very good. Part because they were done without data, and part because they're just not very good. And so you know, so now it's the moment to try and understand this, and I don't. But I'm going to try and tell you what I don't understand, which is most of it. So so the objective. So if at the end of the class, so just you know, it's always a good thing to lower expectations. If at the end of the class you're hopelessly confused, I claim total success. Okay, so I just want to confuse everybody here. Okay, so let me start. So let's start. Yeah, so I'm not going to talk. I'm going to talk a little bit about my own work, but not about my current work. In part, I don't know. Maybe at the end, if I have time at the end, I'd love to talk about it. Of course, everybody likes to talk about what they're doing. But you know, but it's okay. It's really very interesting. But I'm more interested in the stuff that I'm not yet doing, and I will be doing possibly soon. Okay. So let me try and do that. So let me try. So where do I start? So don't look at that. I'll tell you when to look at the slides. So let me try, you know, we often start with definitions, okay? So let me try to give down a definition of culture, which is bad. There are a million definitions of culture, they're all bad. So I'm writing one down to claim it's bad. It's a general one, but I'll try, you know, you understand things about why is it bad, or hopefully you understand things about why it's bad, right? So I want to say that culture is composed of components, those components of preferences, attitudes, whatever this means, beliefs, which, and this is the crucial point, which depend upon the capacity, yeah, this is not good English, but whatever, of, and here is the crucial thing, social learning and intergenerational transmission. Okay, so let's look at this a little bit carefully. Okay, so what am I doing? I'm essentially specifying a little bit what's the object of culture, of cultural studies. Okay, so I'm after studying preferences and stuff which are around it. Okay, so attitudes and beliefs. This is just a way of saying, look, it's preferences, but not really just risk aversion, or it's all sorts of stuff. Okay, so it includes norms and a bunch of things that are hard to define or to list. Okay, so preferences, attitudes, and beliefs, I want to claim, includes everything that could be the object of cultural studies. But the crucial thing here is that which kind of preferences, attitudes, and beliefs am I interested in? Everything, well, culture is in some sense defined through the transmission mechanism. Okay, so it's this idea that you know, a preference is culturally determined when it's transmitted in some sense from parents to kids, or when, you know, you kind of imitated, learn it, do stuff with your peers. Okay, so why is it so? So first of all, this is an important point. I think the issue, culture is a dynamic issue. It's about, you know, learning or forming preferences, okay? Forming that stuff, preferences, norms, and blah, 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 okay? So it's about this, but there's more to it. This in some sense, and this is what I really don't like too much about this definition, though historically it's crucial. This is implicitly defining culture as not genes. Okay? It's saying, look, it's this stuff that gets transmitted, but through a social mechanism, not really through, you know, just because your parents. So that when we talk about intergenerational transmission, we mean something which is purposeful. Okay? So where the parents say, look, you have to be Italian, you have to like soccer. Okay? So that's the intergenerational, or you have to be patient. Okay? So that's the intergenerational transmission I'm talking about. It's not about, you know, picking up your parents' genes. Okay? So this is really what this definition does. And I think this is a little bit of an issue. Not because this distinction is not important, but this issue of nature, nurture, culture, genes is very important. And yet it's probably has been, like Armin said this the other day, I don't remember, I think yesterday, it's probably a badly posed question. It's probably a badly posed question. But it's a fundamental question, you know, that's been posed badly from at least ancient Greece. Before that, surely, but I don't know anything. They didn't teach me anything in school before. So I want to argue that it is very hard, so that in some sense this is why I put up this definition. I think it's very hard to think about formation of preferences and even culture without really dealing with the issue of evolution, okay, of genetic evolution. You know, you can cut it one way or another, but you have to face it. And there are many reasons why we don't want to face it. One is, of course, as I said, that it's an issue that's probably badly posed, and I'm going to argue why. But it's also, of course, because of, you know, it's a delicate thing. So, you know, politically correctness teaches you not to do that. Okay, so I don't care, but that doesn't mean, you know, that I don't worry about saying stupid stuff in that direction. Okay, so I want to, so what I'm going to do today is I'm going to talk also, at least model-wise, I am going to talk about genetic evolution also. And I want to argue, you see, it's there. I mean, it's really, I think it's time we deal with it. And you know, you've seen Armin this morning. You know, is using genetic instruments, let's call it, or whatever, genetic variables to think about culture, but you know, it can't distinguish between culture and genes, and obviously, so you know, it's there. Let's try and think about it. Not that I can, of course, but I'm saying it's there. Let's think about it. Okay, so I want to try and think about formation of preferences, and as I said, I've never done that. Okay, so this is really in part due exactly to his work and work of Oded Galor and other people who are working in this area, which are putting this thing one way or another, are putting the nature-nurture question, even though they don't confront it frontally, but they put the nature-nurture question back on the table. And I think it's right, and I think we should do that. And so that's why I put this definition up, because I don't like it, because it's just trying to distinguish too starkly between nature and nurture. Okay? But what's good about this definition is distinguishing the object, in some sense, from the mechanism. Okay? And it's important. And we want to think about these mechanisms. And I am going to talk today, I'm going to talk about mechanisms today. I'm going to, I should probably list them, right? There's many things, many mechanisms, which have to do now, it's not culture anymore, it's preferences. I'm going to talk about evolutionary models. I'm going to talk about splitting. I don't know, this is not a good word, phylogenetic models, let's call them this way. Okay? Whoops. If you don't know what they are, you'll see. Right? And of course, I'm going to talk about transmission model. What normally is called cultural transmission model. Okay? So why am I making this distinction? I want to argue that these are three different time frequencies at which things change. Okay? Of course, evolution happened more slowly than anything else. Phylogenetic models are about, again, I'm going to not just to get back at him, I'm going to refer to Armin all the time, just because he's been talking about stuff that, of course, are central here. So it's not just that I want to put him like he did to me, but it's just you know, it's unavoidable. So he had this, he was referring to this stuff on and off in all his talk today. So these are models which have to do with the formation, if you wish, of ethnic bundles, of bundles of preferences, typically ethnic, okay? So typically, so you can think about languages, you can think about ethnic, you can think about religion, you can think about anything, but the idea here is preferences come in bundles. I'm going to go back to this thing. Preferences come in bundles, and these bundles separate from each other, differentiate from each other over time. So these are models of how that's happening, okay? So how, you know, you start with Latin, culture, language, and norms, and whatever that is, and at some point you find French, Spanish, Italians, Portuguese, and all sorts. All right? So that's the idea. So how you do that, okay? So people have been doing so. So these models have been, well, kind of everything here, actually. All the models have their origin in biology. The cultural models, too, go back to Cavalli, Sforza, and Feldman, to biologists at Stanford. This stuff has been done in genetic biology forever, and of course, evolutionary models. Okay? So the way economists look at that model is a little bit different. Than biologists do. I have done a lot of work about, you know, putting some economics in here. I think it's, some other people have done, I don't know if it's putting economics, but serious economists have thought about this a lot, much less about this. Okay? So I'm going to present a little bit of, give you a rough idea about how a phylogenetic model works. And I'm going to argue that there's a lot that economists could do there to understand. Okay? So, but again, the idea here is, okay, so this is the slow process. This is a process where bundles of traits, think of ethnic, bundles of traits are formed. And these are processes where once the bundles are in place, let's look at how, you know, the population fractions, the fraction in the population with different ethnic bundles change over time. Okay, so these models are models where the bundle doesn't change. So in some sense, they're faster models, right? So there's a time frame where everything changes. There's another where the bundles change. New ethnic groups are formed. And then there's another where there are a bunch of ethnic groups, and we look at them moving. Okay, moving in terms of not changing what the group is, but changing the composition of the population by ethnic group. Okay, so that's the idea. Is this clear? More or less? So the point here, one of the point here, what's a model, very general, broad view of what's happening here, what you want to try and do, perhaps, is, apart from writing down nice models that you like, models that, you know, explain stuff or that, you know, they're just beautiful, whatever, a part of improving on the models, what you want to try and have at the end, it's a sort of a map between the objects and the mechanism. Right? So it's not going to be a one-to-one thing. Okay? It's not going to be this trait is formed by evolution, this other one is formed by culture, this whatever. You know, the same trait is affected by many processes, and of course, the processes affect many traits. Okay? So, but you want to kind of have a sense of a map. And maybe you want to have a model a broad model about the map. And I'm going to try and give a suggestion, not of a model, but of how to think about this issue. Okay? So what affects what? What does, right? So think about what Armin was saying today, you know, patience or time preferences and risk aversion, preferences over uncertainty. Okay? So very hard not to think that there isn't an evolutionary dimension to that. Of course, there's, as he's shown, not of course, but, as he's shown, different countries which, you can think of as different ethnic groups have different combination of these traits. And of course, cultural transmission, it's all about this. A lot of it's about this. Your parents will tell you, be patient, okay? So specifically those deep traits are certainly, affected by all these mechanisms, different ways, in different forms. And to me, it's kind of important to understand what affects what. Is this kind of clear? Of course, there are traits which are only cultural in the sense that they can't be anything else because they're very recent, right? So, do I like this kind of short or those kind of shorts? That's a preferences. I don't know if it's a cultural preference, but, that's not evolutionarily determined most probably, unless you think about the way generally preferences over things are evolved. Okay? Does this make sense? Okay, so let me try and go ahead. So what am I going to do in this class? So I am first going to go back to some of the things that Armin said and to point out, in some sense, some raw evidence about stuff, things that, I didn't know until a short time ago when I saw these papers. I don't want to reveal when I read them, all last night. So I just want to give an idea about this raw evidence, things that we kind of know, things that we don't, and so on, and see if I can make sense. Now, let me just say one thing also. So I am going to do, not because he's in the audience, and I'm not only going to be talking about Armin, I'm talking about a bunch of other evidence and papers. But the rule here for me is I am going to take all evidence at face value. I'm not going to say, oh, I don't like this, maybe, I could have done it in a different way. I'm going to be very superficial here because the point is, to me, the point is to give a broad view and try to understand what's interesting. Now, if I discover that, he just got all the signs wrong, that's a problem, but I'm going to assume that everything is right and what he claims is correct and what everybody else claims is actually correct, okay? And go with that, okay? So it's often a decent assumption, a reasonable assumption, okay? So the first thing I'm going to do, I'm going to look at evidence. I'm going to look at evidence about distributions of preferences. And then I'm going to look at evidence about, raw evidence again, about these mechanisms, okay? A few things that we understand and know, and then I'm going to talk about models, okay? And then I'm going to try and give you an idea about what's an evolutionary model, what's a phylogenetic model, and what's a cultural transmission model, okay? And I'm going to, of course, to try and map data with the model and essentially say that models are not that good, but that's what we have. We start from there and we try and see, okay? Questions? Oh, and before I go into the models, I am going to give you, I don't know how, well, you'll see, a suggestion of a kind of a general scheme that is used in related fields that might be useful to think about, as I said, the map between the traits and the mechanisms. Okay, so to me, in some sense, at this level, this is really important. So I would like to have a way, because otherwise I can't really write down a model. I would like to have a way to think about what does evolution do to risk preferences that culture doesn't do and vice versa. How do culture how do fast transmission mechanism do to a trait like risk preferences risk preferences or time preferences? How is this trait informed, determined by the interaction of evolution and culture, ethnic, whatever that is? Okay, so I want to try and get there, and I want to try and give a suggestion that it's completely empty at this point. But You'll see. Okay, so raw evidence. So the first so I am very sorry for the et al., but you know, they have 5 authors. 5, 1, 2, 3, 4, 5, 6. 6 authors, okay? So Armin's in the room. I don't know if anybody else is in the room. You're the only author in the room, right? No? Yeah. So, you know, you always cite the author in the room. And it turns out to be the first. Okay, so this is the global preference survey. Okay, so what I want to point out, you've seen this morning, so there's no reason to me to go through details. The trade that they look at are, in my view of the world, pretty deep stuff. Okay, so they're not looking at superficial traits. They're not looking at how you wear your shirts. They're looking at patience, risk-taking, positive reciprocity, negative reciprocity, altruism, trust. Okay, 76 countries, you've seen that. Okay, so this is pretty deep stuff. Deep preferences, okay, which affect all sorts of other preferences for other things that we manifest. Okay, so what do I want to say? Okay, so the first thing I want to notice. Remember, so the idea here, I'm going to take everything at face value, and I'm going to be pretty superficial. Okay, so I just want to point a few things. Okay, in his paper, in other papers, and try to, you know, come up with a sort of a view. Okay. So heterogeneity. Okay, there's a lot of heterogeneity in these traits. Okay, in the population. Look at the population. Look at this trait. 80% of binary comparison. This is by country, right? Or binary comparison are different, okay? Significantly different, okay? So you look at a country, you look at any one of these things, and you know, they're different. This is telling us something, and not only this, but that too, I'll get to this, about bundling, okay? So this is bundling of the traits. This, to me, it's very important because we always thought of, and this is new, okay? We always thought of ethnic preferences as a sort of a bundle, okay? So, you know, Italians dress in some way and eat in some way, okay? And all these things are together in some sense. Of course, there are different levels of intensities and so on, but there's a set of preferences that characterize Italians or Germans. We make a mess, they're precise, okay? So there are a bunch of things that characterize ethnic groups which are, you know, bundled, okay? So that's exactly what an ethnic group means. But this is you might probably don't see. These are pairwise correlation between preferences at the country level, okay? So, and between preferences, what does it mean? It means that there's a correlation between risk-taking and patient, which is 0.2, okay? So it's a serious thing. Serious correlation or whatever. There are some which are close to 0. Negative reciprocity and patient is also 0.2. Okay, so the fact that the bundling, let me say something else. So I'm thinking of a country as an ethnic group. This is not, of course, it's not right, but we could go back, but roughly this is a sort of aggregation. Okay, so. Of course, a country could have many ethnic groups, and 2 countries can have the same ethnic group. But roughly, I want to think of this as representing some sort of a aggregation over ethnic groups. Okay. So the point there is that the fact that bundling happens at a deep preference level, it's not obvious at all. Okay. So he somewhere in the paper, it's there. He finds, for instance, they find. That Germans are more patient than Italians, okay? And, you know, there's another paper, we discussed this, there's a paper which studies, does an experiment in Meran, which is a city in Italy, but it's in South Tyrol, they are German speaking and so on, and, you know, there's a bunch of Germans, a bunch of Italians in the same city, they go to the same school, the environment is the same. You look at them and you find out that, you know, Germans are more patient than Italians, the kids, okay? So, I would not have said that, okay? So maybe I would have, but it's not obvious. that, that there is such that you can find systematic effects of this sort. Okay, so to me this is very important. Okay, and of course it's pointing at something because ethnic groups are ethnic groups. They cannot be defined, in some sense they cannot be defined, or, well, not true, but ethnic groups are formed at a faster speed than genetic evolution. Of course you can think that all ethnic is genetic too, but in my view of the world, if something happened at the ethnic level, it's a little faster than at the genetic level, than evolutionary level, okay? So I want to think that in some sense this says that the ethnic level affects deep preferences in a way that it's not obvious. I mean, you could have perhaps guessed, but it's not obvious at all, okay? So the important thing is, of course, heterogeneity and bundling, and then, of course, the other element is the variance decomposition. Well, the variance decomposition is the measurement. Let's say the between variation, right? That you measure through a variance decomposition. Now, we have to be a little bit careful here. So, for instance, in the paper, they found that for patients between it's 33.5% of the variance, and within it's 86.5. This is for patients, and for risk is 991. Okay? So answering a question, Armin said, look, there's a lot of within variation here. Okay? So there is some between variation. Again, the between variation is what I claim it's come from here. It's important, the bundling and so on. So there's a sense in which one country is different from another at the level of this preference traits. But there's also a lot of within variation. Okay. Now, to make this so you shouldn't be. So my first reaction is, okay, so this stuff is kind of irrelevant, okay? So it's all within, it's mostly within, and it's within that we should care about, but if it's within, I have no idea what this is, okay, or very little. About this, I have a little bit of an idea because I have all this, at least theoretically, I mean, because I have all these models about formation of ethnic groups, but about this, not really much. Now, you have to be a little bit careful in this decomposition in the sense that this is raw. As Armin noticed, this preference trait vary in a systematic and clear way with age and with all sorts of other, demographic and other characteristics. So a lot of this variation has to do with that, okay? So you could compute, I don't know, whatever, this various decomposition with respect to patterns, age patterns, and then of course I guess the between would be larger as a fraction of the whole variation, right? So so we have to be a little bit careful about what this means, but this is an important result here, okay? There's a lot of variation with it, and we really have, I don't know, apart from drift, so just mechanical genetic models. I don't know of models, I don't know of theory which try to get at this. Okay, so it's a big deal. Questions? Now this is not, so this element that I'm stressing in the global preference service are by no means only there. So this is a picture from a paper by Fishman, Jacquiela, and Karif. So let me get rid of the very different thing. This is a political economy paper, so, you know, comes from a different word. Fishman, Jaquiela, Karif. Also this year, okay? So let me tell you what they do. They have this is an experimental paper. What they do essentially is they give choices to people. They assume that people have a utility function of this form. This is the fraction of whatever, a pi, that you give to yourself. Let me just say, to yourself, S is for self, O for other. The utility function is something of this sort, alpha. So it's a CES, two parameter CES. No, this is, of course. Yes, that's correct, sorry. Rho, 1 minus alpha, by O to the rho, the whole thing to the 1 over rho, right? And so people, they have this thing, how can I say, this platform, computer platform that they use in experiment, which lets them, which gives people, makes people essentially make choices, okay? So they give $1 to a person, they tell a person you have $1, this is your budget constraint. Given your budget constraint, tell me how much you give to yourself, how much you give to others, okay? So split the dollar between yourself and others, okay? And then postulating a functional form of the utility function this way, they can estimate alpha and rho, okay? Of course, they vary p's, they vary the prices, and it's really a revealed preference experiment, right? So they look at this alpha and this rho. These are also relatively deep parameters. They are, of course, very related to, you know, whatever, all these social parameters that Armin was talking about, right? So they call alpha fair-mindedness, which essentially means, you know, how much more you care for yourself rather than for others, and they call rho equality efficiency trade-off. That's because when rho is less than 0, essentially this agent wants to reduce heterogeneity between self and others. When it's greater than 0, the agent the agent wants to maximize the size of utility, right? The aggregate utility. Okay, so the point, it's not very important what these things are, apart from these are parameters of social preferences. The point here is, look, if you look at the mean is the black dot, and then you look at, so this is the 25th and this is the 70th, so these two dots are 25th and 75th percentile, and the mean is in the middle. In the other figure they have the median, I don't know why. But you see that even if you look at this, so the way they present the data is this, right? So look at, where is it? Protestant, okay? So let's look at a cultural trait. Religious trait. You look at Protestant and you see, you know, there's a lot of variation. So the distribution is very unequal. Same for Catholic. Okay, so you pinpoint. I'm not sure this is the best way to, you know, to argue, but it kind of goes in the same direction in some sense of the stuff that I said before. There's a lot of heterogeneity, so things depend. There's a lot of heterogeneity in data. There is some bundling in the sense that, you know, these characters, Catholic versus Protestant, matter. Sorry, there's another picture which refers to equality efficiency trade-off, and you see a similar thing. Okay, so here the idea is essentially the same. Okay, so there is some bundling. This character depends on a bunch of stuff, of course, age and all sorts of things, but also depends on ethnic or religious characteristics, but there's a lot of variation around. Okay? And so I want to claim that, you know, it's essentially the same thing. Now this is done, it's far from, you know, carefully done, but because that's not the object of their paper also, but it goes exactly in the same direction. Okay? So there's a bunch of other things that we might want to cite. Of course, which goes in similar direction. All right, so this, this is this famous paper, when the year, I don't remember what the year is, 01, I guess. So this famous paper where, a bunch of economists, anthropologists, and whatnot went around in underdeveloped countries to especially, to groups, tribes, ethnic groups, people living in different, economic conditions. I mean, not just economic in the sense of richer and poorer, structural. There are hunter and gatherers. There's all sorts of stuff there, and they do standard experiments, right? So for this paper is about the ultimatum game, okay? And so what they do, of course, what they find is enormous variation, very large variation in the answers that people give. In particular, for the I have it here, for the ultimatum game, one way in which you can look at the result is what are the mean offers, right? So the ultimatum game, you offer, you're given a dollar, you offer a split to the other guy. If the guy accepts, you do the split. If the other guy rejects, it's gone. Okay, so as you all know, the equilibrium is to offer next to nothing or nothing, and in fact, people typically offer stuff because people reject, the other people reject. So while they argue, I don't actually know this, is that the standard results in experiment, the average in experiment is about 44%. The offer, they find things from 26 to 58, whatever that means. Okay, so, but again, so this is the idea here is also to try and understand, so it's not very clear which preferences they're looking at. It's a little, it's really confused. But at the same time, again, the thing they point out is this variation, okay? And this is, I actually haven't checked whether they report something about individual variation. This is cross groups variation, right? But, okay, so there's other papers of interest. The second author, Ortuño. So these people have done a lot of work, especially Romain, have done a lot of work in this area. So what these people do is something, this is the paper which in some sense gets closer to the social survey, global social survey, global preference survey. So what they do is they look at the world value survey. They have a bunch of interesting results there, right? So they look at the world value survey. Essentially, they do, so they do an OLS of answers to various questions on ethno-linguistic on an ethno-linguistic dummy, okay? So this is the first thing they do. This is getting at the bundling, what I would call bundling, okay? So they find that, how many? 40%, so there's of course, the world value survey's got, I don't know how many questions, 2,000 actually, it's there, it's here. So 21,000 questions, 21,000 regressions, okay? Because the left-hand side is the answers to a bunch of questions that are asked in the survey. So there are 21,000 regressions, and the share of regression with jointly significant ethnic dymies is 43%. Okay, so this is some sort of a measure. People measure things measure the same thing in different ways, but this is some sort of a measure of the fact that there's bundling, okay? That the ethno-linguistic variable is important. At the same time, where is it? Nope. I destroyed my joke. Okay, so it was here. I just can't read it right. Where is the thing? No, I just lost I didn't put up the table I wanted to do. So the other, oh yeah, because it's afterwards. Okay, sorry, nothing. So you'll see that so I'm going to talk about it later on. I don't know why I put it later on, but in any case. So the point here is, the point of this paper is twofold. This is about bundling. It's about ethno-linguistic dummies being significant to explain the answer to these questions. And the second part is about the fact that the variation in culture, whereby culture is defined as some sort of answering of those questions, right? So the variation in culture, it's not really related that much to the ethno-linguistic fractionalization. So once again, so they're running essentially a measure of diversity in culture that they construct. I'll tell you how they construct it later on, but they run a measure of variation in culture, and they run it against ethnic linguistic fractionalization, variation in ethnic and language groups, okay? And they find that there's not much correlation. What does that mean? Goes back to Armin finding about within between, okay? So we're back there. There is some between variation, which is this, the bundling, but there's a lot of within variation that trumps everything, okay? So when at the end you try and see whether your ethnic group affects the variation in the ethnic groups, affects the variation in culture, which is in the way you answer this question, you find very little or nothing, okay? Because again, the within variation is trumping everything in, okay? So essentially this is, yeah, so essentially this is, I started at 1:30, okay. This is the point that, to me, this is the point that comes up from this literature, okay? So bundling is there and it's important, and we want to think about that. That's why we have these ethnic models or models about ethnic groups that I'm going to talk about. At the same time, though, there's a lot of noise, okay? So at this point, it's noise because I don't know how to think about it, okay? So this is really one of the first things that I want to claim, okay? So I think I know how to write down decent models of the, things happening at the ethnic level. I can do stuff about evolutionary models too, but all this variation within, all this noise, it's hard to account for, apart from going back to drift, right? So to genetic drift, that I don't think, it's a residual really. I don't think we want to go there, and it's exogenous. We don't know anything about it. Okay, so let me talk a little bit. I'm going too slow, but let me talk a little bit about some stuff that has to do with the mechanism. Okay. So this came out of what Armin was talking about today. I didn't point it out because I'm pointing it out now, but it's not very deep. It was clear and obvious in what he was saying. So think about the last part of his presentation. So I want to try and understand something about the mechanism. As I told you, I'm thinking here about three general class of mechanism: genetic evolution, phylogenetic dynamics, the splitting of formation of ethnic groups, and then movement, so culture intergenerational transmission given the group. Okay, so this last one is not really relevant for what we're talking about. Okay, so now the really issue now is the nature nurture. As I said at the beginning, this thing comes up crucially. Okay, so when we think about these deep parameters, of course there is an element of intergenerational cultural transmission. We're going to talk about it later, but at this level, at this level of generality, and maybe that's part of that. It's what part of this cultural intergenerational cultural transmission is what underlies what I call noise. Maybe, I don't know. That's something you might want to think about. But let me try and understand a little bit about this, the nature nurture, right? So the evolution versus cultural. Okay, so there are two kind of results that come out of what Armin was talking about, and I'm going to argue that they are there also in other papers. So he was very clear, and I'm talking about the last part of his presentation, the one that you refer to as an ancestry or whatever. So the long time out of Africa explanation for stuff. Okay, so there are two drivers there. Okay, so if you think about genetic variation, there are two drivers. One is drift, okay, as I said, or selective pressures. So it's this idea that, you know, as time goes by, people are different. Okay, so there are mutations and people get to be different just because time goes by. Maybe there's selection too, but just because time goes by, there are differences that are coming up. Okay, so this is one dimension. The second dimension that's happening is, I don't remember if he called it this way, the serial founder effect. Okay, but so this is what he had in mind. It's this idea that in the way in which, you know, people moved, humans moved since the out of Africa, what happened is, you know, they moved from East Africa, a group went, and then they stayed there wherever they were for a while, and then, you know, some moved away, and then from that group, some other moved away, and so on. Okay, so this is the sense in which distance from East Africa is a proxy for genetic variation. Okay, why? Well, the idea here is that if these groups are not too large, and if there is a group standing here and half of them go away, this half has less variability in genes than the whole original group. Obviously, just because you're taking half. Of course, the law, if this group is enormous, the law of large numbers will tell you that it's the same, right? You take, unless there is selection in who moves away, but if there isn't selection in who moves away, you take a fraction of people that are exactly identical as everybody else, if there is no selection. But even if there is no selection, if the group is small, then the people who go away are taking away a bunch of stuff. Okay, so that is the idea, and this is what is called the serial founder effect. Okay, so essentially, when you look at this data, when you look at what left-hand side variable on some measures of genetic distance, of genetic diversity, you're picking up these two things. Okay, you're picking up on one dimension the fact that over time people become different. Okay, so genetic distance, for instance, and the other is that, you know, they become different in a special way. The heterogeneity of genes becomes smaller and smaller as they go away. Okay, so one is a general phenomenon. In some sense, it's a general phenomenon. There's just a, you know, drift. It moves. Things become different. The other one is telling you in which way they become different. Okay, they become different in the sense that their genetic variation becomes smaller. Okay, so it's signed in some sense. So this is, so if you look at this data in the paper I have, Armin looks at risk attitudes. Now I think today he's done it and he sent me the other paper, so he's done it on all the other traits. But the one I've seen is in risk, but it doesn't make a difference, it's everywhere. So what he finds is that if you look at the risk attitude, the differences across countries, the difference in risk attitudes, and you run them and you regress them on genetic distance, you find an effect. Okay? And this is the first of the two effects that I'm going to talk about, right? So the differences are determined by their genetic distance, or the time that elapsed since they split, okay? Again, because the splitting generates this. This is fine, okay? So this we understand, and it's important, and he has a very nice interpretation, which, as we were saying, he can't distinguish between evolution, genetic evolution and cultural evolution, but it's true that, you know, it's perfectly reasonable, and the explanation that he prefers, I mean, I'd love to be able to distinguish, but the explanation that is put forward, which is that this is not necessarily genetic, that, you know, that population which lived in different places for a long time, essentially, you know, they are affected by different shocks, they're affected by different experiences, and so they form different traits, okay? So that is fine, and it's very nice and very interesting. We'd like to distinguish, but it's cool. The other one, the other relationship that he finds, I don't remember if he spoke about it, but the other one that he finds, and I'm going to argue other people find, So this is, let me just put them down so that, right? So this is risk attitude differences by country on genetic distance. Right, so, and you know, and again, this was done very carefully. Genetic distance is measured by genetic distance when you can, or it's measured by distance from East Africa, it's measured by distance from South Africa, all sorts of stuff, okay? So you can be very careful about what the genetic distance is. The point is that there is this effect, okay? And again, this effect can be both culture or evolution, okay? But genetic evolution. But we kind of like the cultural explanation better. The other effect is that the standard deviation okay, so that's genetic diversity, let me call it. That's harder. Okay, this is harder because this, as I said, this is the serial founder effect. This thing is signed. Okay, so here the idea is that the farther you are from East Africa, the later you split, you had this split, the smaller is the variation in your genetic endowment. Okay, so people who are far away from East Africa, far away in terms of not necessarily distance-wise, but you know, migratory distance. Okay, so people who arrived wherever they are later on in time, so these guys have less variation. This has been, you know, less variation in their gene structure. Okay, so this is known, it's measured, and it's a reasonable. There are reasonable measures of this. So these people have less variation, and they also have less variation in risk attitudes. And I'm assuming in other traits as well. So that I don't know how to think about. I really don't know how to think about. And I don't know how to think about it in the sense that you see immediately my bias against evolution. I mean, of course, there is one way to think about it. I guess if you push him, I don't think you even need to put him against the wall. I think you just need a glass of wine, and Oded Galor will tell you that he thinks it's all this, okay? So at least there is one smart, intelligent, good economist who thinks that. I don't know, I mean, my prior is against that, but while this one I can understand and think about, this is really very hard, and it's there. Now, surprisingly, it's there also in a paper by Ashraf and Galor. Okay, so this is, I guess, the first. I'm not really sure. One of the first papers which, you know, studies in detail that thing, right? Where they look at genetic distance and genetic diversity, especially, right? Where they look at genetic diversity, they compute genetic diversity for countries for which they don't quite have data on genes, of course, by looking at distance from East Africa. They do all the work behind, and what they find is that they do a different, so this is Ashraf. They look at number of ethnic groups on genetic diversity. Right? So they don't have measures of preferences, so the measure of preference is much more interesting, but you know, that goes there. So as long as we buy the bundling story, as long as we buy the fact that, you know, ethnic groups are related to different ethnic groups have somewhat different preferences, then we're back, okay? So the number of ethnic groups here depends positively on genetic diversity, okay? Again, same story. Okay, so to me this is another underlying important empirical relationship that, you know, that it's hard for me to think about.
As long as you believe that they created the measure correctly on genetic diversity, because they were using the data on minorities and minorities on the
Okay, so let me say two things. One, first thing is, told you I'm taking stuff at their face value. Okay, so I'm not saying that this is not, of course it's an important question, but so I want to argue that this thing is, as far as I understand now, this thing is out there in the sense that, you know, it's here, it's in FARC, and it's in here, and they're the same, and so that makes me think now. That doesn't mean that you shouldn't go into the details. So let's go into the details. I didn't understand the details.
They were using the data set on genotypes of minorities. For example, for Russia, they were taking Chukchi, and Chukchi is like a very, very big minority, and they are genetically very different from the rest of the country.
Right.
And then they use this measure to create the measure.
Okay, so the way, yeah, so the way they do this, it's, you know, I don't know, as I said, I don't. So the way they do this is they have this data on genetic diversity exactly for populations which are relative minorities, small, and which somehow are still in the place. They've been in the same place for a very long time. So the whole idea here is that you want to look, again, you want to think about the serial founder effect. So you want to go back to when these people split from the rest. So you want to take these fundamental groups and then look at, and then establish a relationship between migratory distance and genetic diversity. So for these guys, you have genetic diversity, you have a distance in migration, you establish a relationship, and then you go back to countries for which, or ethnic groups for which you do not have genetic data, and you impute a genetic diversity measure. In fact, it's called expected genetic diversity. You impute a genetic diversity measure there for these guys who you don't have data on genes on. You impute it on the basis of the distance from the east, right? So you take, essentially what you're doing is you're taking for granted the serial founder effect. You estimate the serial founder effect for a bunch of groups that you can do that well, and then you project this on everything. Okay, so she's saying, you know, this projection is tricky, true. Okay, true. I am sure, though, that these guys are very happy, or will be if they haven't, to see Armin's results. Okay, other questions? Okay, so so let me cite a bunch of other things. Let me cite a bunch of other things. So there's people, so I don't know if I should, whatever. So there's a paper, I've seen a paper. So what I'm trying to do here, as you've seen, is I'm trying to, you know, again, give a broad view of things. And so I'm fishing around in different literatures to try and see if I find interesting stuff. Of course, I'm far from having searched carefully. I just searched here and there. One thing that I found, which I thought was interesting, let me just mention it, is a paper by two biologists, McRae and Terracciano, 2005, where what they do is they try and argue that, you know, if you aggregate by country measures of the big fives, right? So the personality characters, neuroticism, extraversion, openness, agreeableness, and conscientiousness. So if you aggregate this stuff by country, you get measures that make a lot of sense. Okay? And where they make a lot of sense, you know, it's we have to be careful. But the idea, they even make sense. They even have people evaluating. So they would ask you, take you, I don't know, suppose, is there any people from Japan? They take somebody from Japan and they say, So what do you think? Do you think Japanese people are high neuroticism or low? And then they take these measures, then they compare them with what they find by aggregating these measures across people, and they kind of match. So the point, I mean, this is really very loose and not very deep, but it's kind of interesting because of course there's a lot of stuff about the evolutionary determination in terms of evolution of the big fives, and so it's kind of interesting that that you can relate them. I don't think these are very interesting. I mean, I don't think you can use them that much as general national characters, but they're still very interesting that you can find them through these individuals. It's a way of getting, like Armin said today, it's a way of getting at preferences from a different point of view. It's not necessarily better. In fact, I think it's worse, but it's interesting that you can do that too, okay? So I just wanted to cite this. Okay, questions. This is a natural moment. So I'm going to switch now to theory. Okay, so what I want to do, I want to argue. So let me take stock for a second. Okay, so what did we learn? We learned that there's a fundamental dimension. So if you look at the distribution of preferences over population, there is some relevant variation between. And there is a lot of variation within. The variation between, I want to argue, is relates or is a way to could be a way to conceptualize ethnic preferences along ethnic groups. Okay, there is more than that. There is also quite a lot of evidence. It's not tight because there's a fundamental identification problem. But there's quite a lot of evidence that the split, that the determination of the different ethnic groups matters. Okay, in the definition of preferences. That mechanism is somewhat of an important mechanism. Okay, so what I wanted to argue that this thing does, the first thing does, right? So the fact that preferences depend in an important way from genetic distance, it's a sign that the mechanism of splitting of these groups as they migrated out of Africa matters, and I want to claim this is of course a cultural dimension. Now it's not, of course, it's I have no reason to argue that of course should be there. Okay, so as Armin said, I don't know, it could not be, but it might very well be. Okay, so I want to think of this component, this part of this and the same stuff that Ashraf and Galor find, that this is evidence of the fact that mechanism, the splitting of different ethnic groups, is important. Okay, and so I'm going to talk about models of that sort because the models are not very good, but they could be improved, and I think these are very important stuff. At the same time, I want to argue that there's two things here. One is the variation within, which might be determined by some sort of evolutionary mechanism, for instance, drift, which, by the way, is the same that determines this. So that could be an argument. So there could be that. And there's also some other stuff, the standard deviation of culture and standard deviation of, the relation between the standard deviation of culture and the standard deviation of genetic diversity that points to something genetic too. So also I think it's kind of important to think about these evolutionary models too, because I don't think that from a bird's eye view of the literature like the one I've done, very hard to exclude genetic stuff, right? Even when we want to, very hard to. So here we can say, oh no, this is all cultural. Maybe. We don't know, but let's buy that. But still, this is very hard. And so I think we should think about this, and we should seriously think about try and understand what evolution does and what culture does, and so go back to some sort of a nature-nurture. Now, the sense in which the nature-nurture question is badly posed and I think it is badly posed, the sense in which that question is badly posed is that the way people typically look at that question is they do some sort of a variance decomposition between changes in the environment, and so it's a linear decomposition. There's all sorts of problems, okay? And there's no reasons why the computations that people normally do to understand that, by using, for instance, identifying stuff with twins and twins reared apart and this kind of stuff, that thing is solid. But I have no doubt that we should try and think about integrating models which integrate evolutionary dynamics and cultural dynamics. Okay? I'm gonna now, so questions. Come on, ask some questions. Oh, yeah, so I screwed my, so this was, because I'm essentially done with figures, there's a few more afterwards, I wanted you to look at something nice and related to where we are. Okay, so, and I forgot, and so I did a mistake twice. First by presenting it first, and then by not putting it up. So just have it there. Okay, so are there models? Yes, Steve. Thank you.
You may want to defer this or ignore it.
Yeah, no.
Could you say something about timescales? In other words, should we think about cultural evolution and presumably biological and cultural are function in different timescales?
Yes, yes. So the way I want to distinguish the mechanisms, as I referred to before, is exactly by time scale. Okay, so now I won't give you numbers, but as I said, so the idea here is that there is a slow movement which is evolution, whatever that is. There are a lot of discussions about can be faster than we think it is, and so on. So that's the sense in which I'm not going to take a stand yet unless we discuss any specific things. But so there's something very slow going on there, and then there is something which is happening essentially in the last 50,000 years, which is out of Africa. So the splittings. Any one of these models of the splitting of cultures, of course, the farthest back that it can go is 50,000 years. Okay, so that's the scale there, and then there is the scale of given the cultural traits, interaction between populations and different cultures. This, of course, is much faster. Okay, so this is, I don't know, the last, since agricultural revolution, I would say. So roughly that's what I have in mind. So most of the models you'll see, I'll put up a model of phylogenetic dynamics. So a lot of these models, in fact, look at, for instance, this is on language. This is one of the basic. Language starts back from the Indo-European. In fact, the whole point there is the Proto-Indo-European language. So the point there is exactly to dating the beginning of, the first split from the Proto-Indo-European. They dated in 9,500 before the present. Okay, so that's the idea. So this is a little bit the time scale. Of course, evolution is much slower. Okay, so exactly. So let me start from here. So how do we think about? I have no clue. How do we think about this interaction between evolution and splitting? Okay, so let's forget about the cultural transmission proper, the thing of you talking to your kids. That, I don't know, we know better. It's easier to do, and I've done a lot of work on that, exactly because it's easier. But let's think about evolution versus splitting. Okay, so what determines what? I have no clue. The way typically people think about this is they take a trait and they look at proportions of that trait determined one way or another, proportion of the variance of that trait, and that's okay. But this is a very structural way to think about. Okay, so you look at IQ, you look at preferences over time, and you say, okay, of this variation, this fraction is genetic, this fraction is is cultural or due to the environment, but what does that mean? It's looking at this trait as a whole and splitting its variance. It's okay, but it's a very astructural way, non-structural way to think about it. So I've been thinking and looking around in the literature for people, environment models of stuff that resonates a bit more and that seems more, theoretically advanced or theoretically ambitious. And one of these things, and I'm just going to throw it out there because I think there's work to be done here. Just throwing it out. So people in linguistics have been thinking for a long time about, and again, the name is always Chomsky. So you go back to Chomsky. He's been thinking, and people after him, of course, but he's been thinking about this thing that he calls principal and parameter model. Okay, what's the principal and parameter model? Okay, so the idea here is that, let me just read, if I have it. Yeah, so principal and parameters, P and P, it's a model in generative linguistics where the syntax of a natural language is described by general principle, abstract rules and grammars, and parameters which are characterized in particular languages. So the idea here is, look, there's a universal grammar, there's a universal language, okay, which is a set of rules, of general principles, grammars and rules, which are the same for every language. And then specific languages are, so there's a structure, if you wish, a model, a general model of what is a language. And these models is a bunch of parameters which are free in the sense that they are picked up by specific languages. And this is also a way, in their view, it's a way in which kids learn a language. Okay, so kids are born, they can learn any languages they face, and what they do is when they listen to their parents and other people speak, and they fill these parameters in. Okay, so the parameters of the principle. So stupid example, simplest possible example. The idea here is think about the structure of a language: subject, verb, object. Okay, so this is kind of, I'm not sure this is true, but suppose that this is part of the generative grammar, right? So this is a universal. And then, English is a head-first language. So the subject comes first, before the verb. And Japanese, I'm told, is a head last. Okay, so the verb, the subject comes at the end. Okay, so this is so it's very important, of course, what's the subject and what's the object to distinguish a language, right? So to distinguish what's happening. So in some sense, the kid is learning, the first thing that I hear is the subject. Of course, there are all sorts of exceptions to the rule, but the first thing I hear is the subject, okay? So in English, and the last thing I hear is the subject in Japanese. And so the idea here is, you see what I mean? The idea here is that there's a general structure, and there are parameters that gets to be fixed by specific languages. So one way in which one general, and I have no reason to think this is the case, but a general model that one can think about, general structure, general vague model that one can think about this interaction between evolution and culture is exactly this. Okay, it's this idea where there are general structures that are determined by evolution. Think about preferences for risk. Okay, and then in the sense of a specific form of preferences or a preference over time, even the concept of time, if you want. And then there are specific parameters, which are the values of the discount rate, roughly, that different ethnic groups associate. Okay, so Germans are discount less, and Italians discount more for some reason, right? So the issue here is, of course, how is it that one language, one ethnic group fixes one set of parameters and not another? And of course, has to do with, you can write down models of the formation of parameters or formation of ethnic groups. Okay, so this, I'm not saying that this is compelling in any way, but to me, by looking around, this is the only interesting way I've seen to think about this relation. Okay, so this idea, and I'm going to talk about models now, which you can fit to, or you can play with to using this form. right? So again, so this is just, I'm just throwing it out there. It's this general idea that, you know, it could be that evolution defines the structure and the parameters are determined culturally. Okay, yes?
So I had one question about these empirical studies on language. So many developing countries have like English or Spanish as official languages. So how are these countries treated in these studies? I mean,
There was?
How are these developing countries treated? I mean, which language is taken in these empirical studies?
Which empirical studies?
Well, the empirical studies that you cited that claim there is a relationship between language and development or something. I mean, do they use indigenous languages of the development?
So I didn't cite any. So I spoke about languages to say that, you know, these linguists have this idea of principle and parameters. I didn't cite anything in reference to languages and development. What I'm going to do is I'm going to show a model of the formation of languages, of the splitting of languages, right? So this is a model in this particular, so they do everything, all sorts of stuff. I'll show you how it works, but in this particular case, this is a model of the formation of all Indo-European languages. The data is essentially a bunch of characteristics of the end of this process, which is the languages as we see them now, and then a bunch of characteristics in the middle. So some languages that we know a few things about, like how do you say Hittite? The language, Hittite. Okay, it's Hittite in Italian, so I know. So right, so you have a bunch of data in the middle that helps, of course, identifying the time frame, how quickly the stochastic process moved. They have a bunch of data at the end, and you try to understand when the splitting happened. Okay, but that has nothing to do with development for the moment.
You know, I mean, it doesn't have to be development. It can be other outcomes,
can answer your
references
question.
or something like that. Yeah. So I was just wondering how you would.
The ethno-linguistic studies actually are from Soviet linguists, and they're roughly speaking based on the language that one grows up with. And it's very rare that you can identify the family language. So in the case of India, English may function as the lingua franca for the educated class, but that would not be counted as the language for individual families, but the family spoken home.
Okay, so yeah.
So the way these parameters are being selected is in linguistics solicit. So it's like every parameter is independent, or there is like an order of the parameters, and the choice of one determines the set of things that you can add.
So very interesting. Okay, so there is a very different. So these guys, the Chomsky, this principle and parameter stuff, these guys are completely theoretically minded people. So they don't ask that question at all. What they've been doing for 40 years is to identify a bunch of principles and a bunch of parameters. And every time somebody comes up with a new language, which doesn't fit this structure, they modify this. So their modeling is, so there's no modeling of what gets selected when. There's this general model of how what constitutes a language, and the way in which data is used for this model is new languages, right? So if we discover that it's not for all languages, it's not true that every language has a subject, verb, object structure, then of course if that was a principle, now it's not a principle anymore. So you have to go back again and construct something which is more general than that, and that becomes a parameter. You see what I'm trying to say? So the whole point is to get to this very general principle which are the same for every language, and everything else in some sense is a parameter. How do you, I don't know that people have looked at when is it that these parameters is fit in yes, Stephen?
I'll give a stronger defense to Chomsky, but that may be a diversion.
Go.
I mean, the notion of universal grammar is that there are certain commonalities across all human languages that are actually have to do with neural structure.
Right.
And as an example, is there's no language has the structure that you use the words in order of their length. So in other words, and so so that's the sense in which they would claim they verified aspects of universal grammars or things they can rule out. The identification problem, so Chomsky's idea was that actually This is very revolutionary. The mind's not a blank slate. The way we think is in the neurons, and language is part of it. The classic argument is exactly what Alberto said, which is that children learn language so quickly and are able to innovate with new sentences they've never heard, that he was able to explain why behaviorism wasn't satisfactory for language acquisition. The identification problem is that the assumption is the brain has a certain structure, that's the principles, and then the parameters, which are very broadly defined, are determined by context. The identification problems, it may be the evolution of languages that certain principles, there are many possible principles, but there's convergence because of efficiency. But from the perspective of Alberto's work, actually that identification problem is irrelevant.
Right. Now, by the way, what Stephen said is important. I haven't said it, but it was in my mind, which is the fact that the principles are somewhat genetically determined. It's why I thought this could be, in some way, a model of what I'm talking about, right? So the principles are the genetic components here, right? So the principles are determined at the level of genetic structure. The rest is culturally determined, okay? So that's why I'm thinking about this distinction where outside of languages, possibly, okay? Where, you know, there's something which is determined. So we think about risk in some particular way. We think about time discounting in some particular way. How much we discount is cultural, okay? But the way we think about time, possibly, is genetically determined, okay? So think about, now there's another element here which is important, which is the same here. So notice one thing that Stephen said, which is of course in Chomsky, is this idea that, you know, there's a universal grammar. It's unique, okay? So, I mean, it's one structure. So, and this, I don't know, I mean, this goes back to a lot of the evolutionary models. So a lot of these models have in mind that, you know, evolution determines something which is not heterogeneous, okay? It's fixed. So there is one way to think. There is one universal grammar by construction, right? The genetic structure of evolution determines that, okay? So, and a lot of the evolutionary models of preferences have the same property. So all the heterogeneity is in the culture. But, you know, there's one way to think about risk, which is a parameter of risk aversion, suppose, right? That we want to model as a parameter of risk aversion. That's the way. So the idea there is, you know, we think about risk that way. There's a parameter. There's a utility function with a parameter. What is the parameter that depends? That's the idea here, okay? So it's at a very vague sense in terms of analogies. This makes some sense, I think, okay? And then we see. So now I'm going to start talk. So unless there are questions, I'm going to start getting to models. So given the hour and a half introduction that I had on empirical stuff and the general view that I have about these issues, let me give you now. So what I want to do in this brief time, the only thing I can do is I can give you examples of models at different time frequencies that models of, you know, formation of preferences, okay? And these models have not been derived in the same, now following the frame of mind that I suggested we might follow, principle and parameters, for instance, or they have not been driven or derived to think about the new data that Armin and others have put forward. So these models are necessarily not that good, but you know, that's what we have. So the point here is I want to give you an idea of the classes of models that one can use and play upon to think about these issues. And I'm going to try and stress, you know, what are the problems, how can they be extended or corrected or thought about. Okay, so have three basic groups. Evolutionary models, then I have, as I said before, then I have phylogenetic models, and then I have cultural transmission models. Okay, I will spend most of my time on the first two because perhaps they're less known. And the cultural transmission is what I mostly worked on, so I'm also more bored about it. So I'll talk a little bit less about those, okay? And if I don't have time, I will not talk at all about those. But you know, the economists know those kind of models more, so it's not that big a deal. Okay, so let me start by thinking about evolutionary models. Okay, so what about this? Oh, by the way, so a lot of what I'm going to say here comes from a beautiful survey paper by Arthur Robson and Larry Samuelson that appeared in the Handbook of Social Economics that I edited with Jasmine Habib and Matt Jackson. So it's a very well done, it's a long survey, very well done, very interesting. So let me pick at least one paper from there, a couple of traits or models from there, and then I'll give you another model that I've worked on a long time ago. Okay, so let me give you a general, I mean, 2 lines general overview. Right, so these are models where we tend to maximize fitness. Okay, so what this means depends. And what the maximization process is depends, and how you compute fitness and things of this sort depends, but at the end of the day, this is what the models do. Okay, so we suppose that there are issues with local maximization, global maximization, there's all sorts of issues, but roughly what these kind of models do is they write down an environment and they have fitness determined as a function of this environment, and then what we assume evolution does is it maximizes fitness. All right? So now, in some sense, what we are trying to understand here when we say, how do we think about these models in terms of how do these models tell us, give us information about preferences, what they do is, well, they characterize, it's a way of characterizing fitness, okay? So what we do is, in a lot of this model, not all of them, but in a lot of this model, what the utility function is fitness, okay? Roughly. You'll see the examples, okay? So it's not exactly this, but roughly that's what it is. Now, it's not always this. It's not always fitness, in part because, in some of these models, for instance, the whole idea is that we don't really know, that agents, humans, don't really know precisely, or they are prone to biasing or to put constraint on the relationship between whatever they choose and fitness. Okay, so you don't directly choose fitness typically, you choose a bunch of stuff, you choose how much you eat, and the map between how much you eat and fitness and many other things, it's complicated. So sometimes what the characterization of this model is about, constraints on, you cannot really maximize fitness. You maximize something which is related to fitness, not quite fitness, because you can't, because you don't have the ability to do that, because there are constraints in your maximization problem. It's what you can choose, how detailed is what you can choose, and things of this sort. Right? So suppose that, 2 different kinds of red meat have different effects on fitness, but you can't distinguish between them. If you can't distinguish between them, you can't distinguish between them, right? So then maybe maybe evolution will make you indirectly distinguish between them through something else, and you don't know what you're doing and this kind of stuff, right? So then, in a situation like this, you write down the constraints, and you try and understand what is this object, which is not quite fitness, but it's related to fitness, which maximize fitness under constraints, okay? So, but the first model we're going to look at are models where we really maximize fitness, okay? So to be consistent in some sense with what I was talking about before and what Armin was talking about today, I'm going to think about evolutionary models of risk attitudes and also of time preferences. Okay, so it's kind of interesting to see what you can say about these properties, these characters. Okay, so these are examples, of course. You'll see in a second. They're just supposed to give you a sense, a flavor of these things, and then I'm going to try and map them to what I was saying, because in my story, in my structure, what these things determine, what evolution determines, is the principles, not the parameters, right? Now you see that in these models, they typically also determine the parameters, and that's because the model is an example, is not general enough. But I'm gonna get to that point. Okay, so For the moment, let's just stick to, trying and understand the general lines of a model, of an evolutionary model which is telling us something about risk preferences. Okay? Is this clear? All right, so the structure of the model is very simple. Okay? So people, agents, or types are lotteries over a bunch of outcomes. Okay? So each one of us is a lottery over a set of outcomes, C1 to Ck. So there are k outcomes. Each one of us, it's a lottery over this. Okay? So, and then of course we're looking at which lottery wins. Okay? In fitness. So to each lottery, it's associated to each component of the lottery, it's associated. So these lotteries have probabilities QK. To each lottery is associated fitness. Okay, not to each lottery, sorry. To each outcome of the lottery, it's associated a fitness value. Okay? So I go left 20% of the time, right 80% of the time, and if I go left, I do 2 kids. If I go right, I do 7 kids. Okay, that's the story. And I'm that type, and then there are other types which go left and right with different probabilities, and we're looking at this. Okay, sorry, yes, which go left and right with different probabilities. Okay, so what is the utility function in this world? Okay, so how risk averse are people supposed to be in this world? What does evolution selects in this world? I can't move it. What evolution selects, so the crucial result here, which is a very interesting result, ex ante, I think you would not have said, is that the crucial result depends on whether these lotteries are idiosyncratic or have aggregate risk. Okay? So think of it this way. Distinguish between a world where all the types in the population, so where every agent picks one of these sets, so a world where the law of large numbers applies in the sense that, there's a QK, so if between the people who follow this lottery, in this type of people, then, QK people, a fraction QK of agent has the outcome CK. Okay? In this world, this is an idiosyncratic world. Suppose a world, contrast this instead with a world where, these are the probabilities, but with probability QK, something happened, and then everybody in this type has the same realization, CK. The probability ex ante that that realization was CK was QK, but everybody has it because it's an aggregate shock. Okay? So the crucial result in this literature, in this modeling structure, is that utility functions have different form depending on how the shock, whether the shock is idiosyncratic or aggregate. Now, this is very, I want to stress that this result is not obvious at all ex ante. Now, the proof, it's not that difficult, but ex ante, you should be very surprised in the sense that from the point of view of the individual, why is this interesting? From the point of view of the individual, it's really irrelevant whether the shock is aggregate or not. Okay, so ex ante, I have a probability of a bunch of things, and I have a probability of fitness, okay, of fitness levels. And the fact that everybody else is like me or other people are different, ex ante, it's not obvious that would affect what is the utility function. You see what I'm trying to say? So what I'm trying to say is that evolution here plays a role where it's aggregating stuff. It's not just, there's an externality, if you wish, there's an aggregation mechanism through the population so the environment, the structure of the environment has an effect on the utility function, which is not at all obvious ex ante. Okay? This is a very important point in some sense. Okay, so what are the utility functions? So in the case, so in the idiosyncratic case, the utility function is this. So this is risk neutrality, right? So this is expected fitness. Okay, so the result, I'm going to prove the result. So if this is the word, and risk is idiosyncratic, then the fitness is maximized when agent solve this utility function, maximize this utility function. In the case of aggregate risk, the utility function is it's log. It's risk aversion. Okay? I don't see you surprised enough. It's kind of surprising. It's not, you know, it's kind of a neat result. Now, let's see how it gets. And it's the derivation. I'm not going to derive the details, but the logic behind the result is important. And it's common to all of this literature. So we're trying to understand. I want to try and understand how it goes. Is the result clear?
What is the intuition behind the result?
You'll get the intuition behind the result in a second. Right? But the idea, so what this is saying is that evolution makes you risk averse with respect to aggregate shocks and risk neutral with respect to idiosyncratic shocks. Okay? Yeah.
And these are separate words, right?
Separate what?
Words.
Yes, these are separate words.
So you would never have a heterogeneous population?
I'm not doing that yet. I could try and do that. I'm not doing that. So I have an heterogeneous population, if you wish, over this, but the environment is single. That's exactly what I'm going to say, what I wanted to say at the end, to say, look, you already see that what this is saying is that, you know, this maps a utility function to an environment, right? I want to think of, you know, a world where you define principle and you fit parameters. Now, that world is a world where, you know, what's the environment, where you take the environment as parametric. Okay, so we can try and do that. It's not a very simple step here, right? Because the interaction between the population, we don't know how the interaction works. Okay, so to get there, you know, it requires work, and it's not obvious which way it goes. For the moment, these are two completely different environments, two separated environments. I'm looking at, you know, what evolution implies in one and what it implies in the other one.
Do people discuss at all? So, do people discuss at all how we should think about it? I mean, aggregate shock is something like, I don't know, earthquake, or what is a? I mean, that is not depending on my decisions there, but maybe on my moving decision. But
I mean, nothing here depends on your decision, right?
Well,
There's no decision in some sense.
Right, but what is a? I mean, to map this, say, to differences between countries, cultures, continents, say, it would be good to have an idea of what they think about. Because it could be that if you look around, so I was briefly mentioning this yesterday together with Paola, who you know very well.
Yeah.
She has collected weather data. And it's in particular about weather anomalies. And here's a non-evolutionary, well, a semi-evolutionary argument, I would say. Suppose that anomalies are very substantial versus very predictable. It's intuitive, I think, and we haven't written a model or something, but it's pretty intuitive that if it's very volatile, it may pay off to develop a taste for patience, right? To take more, you know, to consume less to be prepared for the bad times that may or may not occur. If you don't do that, you're either wiped out as a, you know, in the process of selection, so to say, or you have more offspring. I mean, there are various ways how to make sense of it. And it seems that this is what we find.
Yeah.
So cultures with more, that is an aggregate shock in some sense, right? There's an environment that is hitting everybody, and therefore everybody should develop a taste for patience, right? What is an idiosyncratic shock?
So weather is the typical aggregate shock in this world, right? So again, in evolutionary times, when you think about aggregate shock, you think about weather. And by the way, the next model, it's going to look a little bit like, it's not about patience, it's about something else, but it's going to look exactly in terms of how does the volatility of the environment affect the thing. But this is a build-up to that, and you're going to see it in a second. The crucial thing here is that we want to distinguish evolution picking arithmetic averages versus geometric averages, and the aggregate shocks are that. So I'm going to get there. Yes.
What about persistence?
No persistence. Good question. So the next model is going to have persistence exactly because it's going to look at what he's talking about, volatility over time. And so this model has no persistence. This is just distinguishing. So zero persistence. The shocks are IID over time. But in one case, they are also IID over age, and in the other case, are aggregate over.
But there's a separate literature on correlated shocks that are aggregate versus IID that are idiosyncratic, things like that. Those dimensions been explored.
A little bit. So the next model is going to be on. So these are examples, but you will see enough. I don't know that people have actually developed the theory, but it's simple enough. In the end, it's the law of large numbers. So various form of the large numbers. So I'm going to get there. Stochastic processes, but I'm going to get there. So I don't know if people have done it, but it wouldn't be very hard to do if they haven't. But that's definitely the crucial distinction. So there are three distinctions in some sense. Idiosyncratic versus aggregate, and IID over time versus correlation over time. Marco process. Yes, there was another one.
Yeah, I'm just not enough to understand. This is the result, or this is the assumption.
This is the result. I'm going to get there.
And who is deciding that?
Nobody. Evolution is deciding. Yeah. So the question is, what maximizes fitness? Which utility function maximizes fitness? The question is, if you have, which utility function will be such that if you maximize that utility function, you're maximizing fitness. So evolution is thought of selecting the, thank you, I should have said it more clearly. So evolution here, what evolution does is selecting the utility function, so that an agent who maximizes that utility function is indirectly maximizing fitness. Okay? Okay? Is that?
Fitness is a rubber probability?
Yes, you'll see it in a second. Okay? So remember, one is risk aversion, the other is log. Okay? So let me tell you how you look at these models in a very simple way. Okay? So let's look at an example. Okay? So we're going to do this in the context of an example. Let's suppose there are two types in this economy. Okay? There is nah, I don't want to think about two types. So let me, because otherwise I'm going to confuse the whole thing more than necessary. Okay, so let's look at the following. Okay, so let's look at a world where you have two offsprings. Agents have two offsprings with probability a half, and one with probability a half, and the shock is idiosyncratic. Okay? I want to compute fitness for these people. Okay? So the map is linear, it's simple, there's nothing to choose, it's completely straightforward. This is just to give you the intuition of the argument, what's behind this argument, okay? So what is the number of people here? Suppose we start with one guy, there's no real sex in most of these evolutionary models, there's no sex, at least the way economists do them. Biologists are more fun, there's just no sex, okay? So what's the number of people at time t, at some time t, supposing you start with 1, so that's starting with 1, it's not a problem because there is no sex. Okay? This is what it is. All right? Because how do I compute this? This is the law of large number. This is idiosyncratic. Okay? So it's of course it's the usual abuse of the law of large number. But so there's half of people have 2 offspring and half of people have 1. Okay, so people in the end so every period there's 3 halves. The growth rate is 3 halves. Okay, so this is the growth rate. What's this growth rate? This is sum over k, qk, c of ck, whatever that is, or fitness k, right? No c. This is fitness, okay? So k is 2. It could be the state where you have 2 offspring, could be the state where you have 1. Probabilities are a half. That's what it is, okay? This is the growth rate, okay? So obviously, in this world, what you want to do is you want to maximize the growth rate, right? The growth rate is a constant, so that's how the population grows, okay? So anything else, if you're maximizing anything else, you're not going to grow as fast. Okay, so that's what you want to do. This is the utility function. That's the idea. Okay? So look now instead at the same model, the same structure, but where now there's correlation. Okay? So aggregate. So what do I mean by this is that in every period, it's drawn whether this population has 2 offspring of only 1 or only 1. Okay? So now let's compute NT here. What is NT in this model? What do you think it's NT? First of all, NT is a random variable, right? Do you agree? So before, NT was a deterministic variable. It grew 3 to the half to the 3 halves to the t deterministically. This, no, it depends in t times how many ups you got and how many downs you got. In the limit, when t goes to infinity, then half of the times you're going to go up, half of the times you're going to go down, again by the law of large number. But if you have a finite t, then this object is a random variable. Right? So now you can compute the mean. So first let me write the random variable. So NT is 2 to the n little nt. What's the little nt? Is the number of times you go up. Right? And this is a random variable. Is that clear? You see what I'm saying? So the number of people at time t is 2 times elevated to the number of times you went up. If you went up twice, you have 2 to the second, 4 people. If you only went up once, it's 2. Okay? If you went up 3 times, it's 8, whatever. Is this clear? Okay, so this is a random variable because this object is a random variable. So you can do 2 things now. One thing is you can compute the expectation of this random variable. It's not completely straightforward, but it's the expectation of the expectation of NT. It's the same as in the case in the idiosyncratic case. It's 3 half to the t. Okay, but that doesn't quite matter, and this is the whole point that I'm trying to say. So this is the crucial point. Let me compute something else. Let me compute this. Yeah. One second. Right, so why do I want to compute that? Anybody, why do I want to put the log in front? Which is where all the meat is. Because this is a compounded growth rate. I want to compute the average compounded growth rate. That's what determines who wins. Average compounded growth rate. Right? And you see that I have a log in front. Okay? So this object is, because nt is 2 to the little nt, this object is 1 over t and t times log of 2, which converges to 1/2 log of 2, which is the same as log of square root of 2. Okay? So, and by the way, this object is less than 3 over 2. Okay? Sorry, of the log of 3 over 2. Okay? So now, okay, so now, what is the point here? The point here is that in the other case, the growth rate was the log of 3 over 2, was a constant, right? Well, in this case, the constant 2, that's not the point. So the point that I want to make here is that what is crucial in this model to determine who wins is the log of the expected value of fitness. Okay, the crucial point is, why is that? This is because the growth rate depends on the compounding of the growth rates. And these growth rates are stochastic. Okay? Which is this. It's the fact, it's this object, right? So this object is stochastic. The log of nt is stochastic. So it's nt is stochastic, so the log is stochastic. So it's crucial that when you look at these growth models, when you have correlation over time, then in both cases what matters is the geometric mean. But in the idiosyncratic case, it doesn't really matter. Geometric or arithmetic is the same thing. Here, it's completely different, right? So the average mean here, as I said, the mean is 3/2 to the half. But this is not, right? But this is not what you're looking at. It's log of square root of 2. So the crucial point is that you're looking at the geometric mean. And the geometric mean, when the process is stochastic, depends on the variability of the process. Okay? Depends negatively on the variability of the process. So this is absolutely crucial. Okay? This is the reason why when you have idiosyncratic shock, the arithmetic mean is fine. Okay? Utility function, which is the arithmetic mean, which is risk aversion, is fine. Okay? It doesn't change anything. But with stochastic, with the aggregate shocks, what you're looking at is the geometric mean. And when you're looking at the geometric mean, then the variance matter. Okay? Here we set the variance. I mean, we set the model with parameters already defined. But the crucial point is that it's not the same. The solution is not the same. Okay? So the maximization process, the same process, but one is idiosyncratic, the other is as aggregate shock, give you a different result. In one case, it's the arithmetic mean, in the other, or the geometric, which is the same. In the second case, it's important that there's a log in front. Okay? Because the log is determining the growth rate, the accumulation process. So this is the core of the result behind. Okay? And this goes back, I'm gonna go back again to what Armin was saying. So the structure of the environment, it's crucial. Okay? That's what I want you to take out of this. An environment, and I'm going to show you another environment soon, which does a similar thing. So the environment with idiosyncratic shock and the environment with aggregate shock are two very different environments. Okay? Evolutionary selection in these two environments gives you different results. Okay? Period. Does that make sense? Okay, so now the next environment I want to talk about is related to what Armin was saying, which is, now let's think about an environment where the environment changes with a Markov structure. Okay? So think of weather if you want, but think of an environment where you have a the state is low, you have a probability of going up and down, and if the state is high, you have another probability of going up and down, right? It's a standard Markov chain. Okay? So this process introduces correlation over time, and this correlation over time matters in crucial ways. Okay? So I'm going to give you an example where that, but the idea behind this second example is exactly the same, which is, careful, we need to compute the geometric mean. Right? And this is a little bit more interesting environment. There are two types which are running one against each other. So it looks more like an evolutionary model. This is just the intuition behind it. But it looks a little bit more like an evolutionary model. But the idea there is the same. Right? So look at this environment. The environment changes over time, and preferences change in a particular way. And the whole thing is, let's compute the geometric mean, and once you compute the geometric mean, you're done. You have to be a little bit careful in computing the geometric mean, but that's what it is. Right? In particular, when you have correlation over time, you need to compute the station distribution and stuff like that. Okay, so I'll show you in a second. Clear? I mean, clear. Clear enough? I know it's not clear. Huh? I can't go into the detail, but okay. So this is since I have not spoken about anything mine, this is a paper of mine with Thierry Verdier, who's the person I work with on this stuff, which is 2001. Okay, so it's an old paper which I don't think anybody's read. Thierry probably, not me. So that's one of the reasons why I'm giving it. I think it's kind of neat. It's nice, and nobody's ever seen it. It's on economics letters. Okay, so this is a model where there are two agents, A and B, okay? In the sense that there are two characters which are selected by evolution. And then there's an environment, E, which also is A and B, okay? Which is a Markov with transition matrix this. So what does it mean? It means that with probability rho, the environment goes from A to B or from B to A. So there is a switch, there's a change in the environment with probability rho. Probability 1 minus rho, the environment is stable. I mean, stays whatever it is, all right? So every period, the environment either changes or doesn't change. It changes with probability rho, and it stays the same with probability 1 minus rho. Okay? The simplest possible word. So let me talk about fitness. Right? Fitness is capital V for the agent which has the same name as the environment, and little v and big V is greater than little v. Okay? So the idea here is you want to match the environment. Okay? So the highest fit, you have the highest fitness if your name is the same as the one of the environment. That's, of course, is a simplification, right? If your name is different from the environment, you have a lower fitness. Okay? Of course, now, in a world without restriction, what evolution is doing is selecting for people who change the trait condition on the environment. I suppose that's not possible. Suppose you can do it, but it's got costs. Okay? So that, of course, that's the idea. Otherwise, we stop here. Okay? So the idea here is the following. suppose, and that's why, and I'm thinking of this as a so the interpretation that I want to give to this is the following. It's evolution, it's related, by the way. I didn't realize, of course, I was doing this 15 years ago. It's related to what I was saying in terms of principle and parameter. So the idea here is the following. So the way I think about it is evolution is selecting a character of cultural transmission. So cultural transmission in the normal sense, it's a parameter, and evolution is a principle. What do I mean? So the models that I've written down of cultural transmission have this property which we call imperfect empathy. The idea here is that the father kind of likes a kid like himself a little better, in one way or another. Okay, so there are many ways to write this down, but roughly there is a bias of parents in terms of their own trait, okay, for some reason or another. So I like Italian kids, and Armin likes German kids. Okay, so that's kind of the idea. Okay, so the way I'm setting it here is I'm saying, okay, so suppose I have two types. I have one type where the father always makes a kid like him. Okay, so there's no change. If I'm A, I always stay A because my father makes me A. So the whole dynasty is A's. The B's are B's. Okay, that's one group. And then there is another group instead who changes with the environment. But there is a cost. It's not very deep, huh? It's a trivial story, right? So, of course, I'm trading it off. So I either stay all the same, and then every time the environment turns against me, I lose. But when the environment turns in favor of me, I'm happy for free. The other guys, the other group of guys have what I would call perfect empathy. They change with the environment. They're always the same as the environment. But when they need to change, they pay a cost in terms of fitness. Okay? And so now I'm comparing the two, and I want to argue, look, there are situations where the guys, the imperfect empathy guys, the guys who go stuck, are actually winning the evolutionary game. Okay? This, to us, you now understand why we did this. Okay, we had this model with imperfect empathy, and people are saying, what the hell is imperfect empathy? Where is it coming from? We wrote it down because it made sense. And then we thought, well, you know what? It not only makes sense, it could also be selected in some particular set of parameters by evolution. Okay, so principal parameters. That's the story. Okay, so we're trying to find condition under which the imperfect empathy guys win. Is this clear? The story? Okay, so let's look at how evolution selects between these two guys, the imperfect empathy and perfect empathy. And again, the story is geometric means. But here, geometric means are a little trickier because you have the correlation in the environment, right? Because the probability of A depends on whether you start from A or you start from B, right? Questions? So we make a bunch of assumptions. Let me give you the assumptions afterwards. Let me give you the story. Okay, so let's look at the ratio. The ratio of Ni are the imperfect empathy guys, the guys who never change their trait. And the P are the perfect empathy guys, who are the guys who change the trait. So I don't care whether people are A or Bs. What I care about is that are these people the conditional ones who change their trait depending on the environment, or are the people who stay constant? Okay, it doesn't matter to me if they're constant to A or they're constant to B, right? What I want to know is selection of imperfect empathy. So really, I need to see if this thing goes to infinity, 0, or to some number. Okay, and I actually want to find condition under which this thing goes to infinity. Okay, so the whole point is computing that object. Notice that this object is the productivity, sorry, not the productivity, the product. I get to be tired. From 1 to t of f I tau. These are fitnesses, and this is q, the initial condition. Why did I call it qi? Well, yeah, I call it qi because the I is the numerator. Okay? It's the fraction of the imperfect empathy guys that matters to me, okay, or the ratio. So what is this fitness? This is the whole point. It's very easy to compute. So there are four state of relative fitness. Okay, so this is the relative fitness. It's the fitness of these guys. You see that I wrote it as a product with the initial condition. So this is the relative fitness, the fitness of these guys divided by the fitness of these guys, right? And it could be 1 in the case where both the same. Suppose that the state is A and stays A, right? No, sorry. Yeah, so suppose the state A stays A, or, okay, so the one situation is the fitness is the same. No, but, so it means that there's a group with some fitness, the other guys don't have to change. They don't have to change. There is the other state of fitness, which is the top guys are V, and the bottom guys are the big V minus C. So the bottom guys, the perfect empathies, always have the highest fitness. Sometimes, though, they pay a cost. Sometimes they don't, right? The numerator are always either little v or big V. The first state is this, right? These are the possible fitnesses, really. Okay, and then you can write down the matrix, the transition matrix. I don't want to write it down. It's something of this sort, 1 minus rho, rho, 0, 0, and then the 1 minus rho, rho appears in different places. So you write down the matrix. Then you compute, essentially what you're doing is, okay, so then you compute the stationary distribution. So, okay, so this is a Markov chain on a 4-dimensional state, okay? It's a Markov chain on 4. I have the transition matrix, I have the states of the chain, right? So I can do anything with this. I need to make sure that this object, has a stationary distribution. The easiest theorem to make sure that it does is that the transition matrix doesn't have zeros at some level. So that this transition matrix does have 0, but if you take the square of this, it doesn't have zeros anymore. So this means that the matrix is irreducible. So we're fine. We know that it's got a unique stationary distribution and it's ergodic. Wherever you start from, you get to that stationary distribution. Okay, so fundamental theorem in stochastic processes in Markov chain. So I can compute this matrix. I know that it's got a stationary distribution. I can compute the stationary distribution. It's very easy. Okay, so there's it's 3 linear equations. So I can compute the stationary distribution, which is this. It's 1 minus rho over 2, rho over 2, rho over 2, 1 minus rho over 2. So how do I interpret this? Okay, so the interpretation, I'm just going quickly, this is a relatively basic stochastic process. It's not, if you know it, it's trivial. If you don't know it, it's not important. Okay, so the important thing is that, there are techniques, you compute this thing, you arrive here. What is this? This is important, what is this? The stationary distribution has a nice interpretation, which is, if you run this process for an infinite number of periods, this is the fraction of period you are in state 1. So 1 minus rho over 2 fraction of times, this is the fitness, the relative fitness. Rho over 2 fraction of times, this is the fitness. Okay? Rho over 2 is this, 1 over rho over 2 is this. So now it's very easy to compute the geometric mean. Is this clear? What's the geometric mean? What is the limit of the log, the thing that I want to compute? The geometric mean now is, yeah, I'm doing something people should not do. Never do this when you teach, which is to play on what you wrote, right? What is the geometric mean? It's this to the 1 minus rho over 2 times this to the rho over 2 times this to the rho over 2 times this to the 1 minus rho over 2. Right? Is this clear? Right? You're staying here this number of period. You're staying here this number of period. Here this number of period. Here this number of period. That's what your growth rate is. Okay? So this is what evolution is maximizing. Okay, so this is what drives who wins in this economy. Right? The evolution is maximizing either the numerator or the denominator. So if the numerator of this product is bigger than the denominator, means that this thing goes to infinity. This object goes to infinity, and the imperfect empathy guys win. Is this kind of clear? Yeah. So you see, this is the average growth rate. It's as if every period that's how we grow, right? And this is the relative fitness, it's the ratio of the two. Before, what I did was you need to compare the geometric mean. The guys with the higher geometric mean win. Here I'm writing the ratio, it's the same. The guys with the higher geometric mean win. And so the guys with one geometric mean is in the numerator, the other is in the denominator, right? So the guys with the higher, if the numerator is higher than the numerator wins, okay? And so you can find conditions under which this wins, okay? And the story, of course, is, not surprisingly, that you need enough variability. Rho needs to be high enough. Of course, you need some relation between the capital V and the little v. They have to be such that, you know, also they have some restriction there, but the crucial economic restriction, important intuitive restriction, is that there needs to be a lot of, the environment needs to fluctuate a lot. It goes back to what Armin was saying, right? Logically, right? That the volatility of the environment is crucial here. And so R is the probability of switching. If R is high enough, this thing works, and imperfect empathy guys win. Why? Because if rho is high enough, this perfect empathy guy keeps throwing away C every time. Right? They have a cost to adapt, and if the environment changes too much, that cost is too much, and they lose. Right? And on the other hand, the other guys, you know, half of the times, or a good amount of the times, they are fine. They get the high IV, right? I big V, the capital V. That's the story, right? That's the logic of the story. Okay, so to me, this is, you know, independently of whether you care about imperfect empathy or not, or whether you care the way we wrote it down, this is the logic behind a lot of these models. You compare geometric means. Now, geometric means of what? Well, if you do not have, and this goes back to what Stephen was saying. So, if you do not have correlation over time, geometric means is straightforward. If you have, in the sense that it's actually the geometric mean of exogenous objects. If you have correlation over time, then you need to compute a station distribution, and then you look at the geometric mean over there, right? But that's the whole thing. Is this clear? Okay. When do I finish? At 5, right? Okay, so that's the problem. All right, so okay, so you can. So this is some of these models. Now you can make these models a bit more, as I was saying, right? So this is a good example of the principal parameter story in some sense. Right? It's essentially saying there is a general feature of how traits are transmitted. This general feature is perfect empathy versus imperfect empathy, and this general feature depends on the environment. Okay? So I want to try to argue that. Okay. So then, okay, so for instance, we have a bunch of models, a bunch of evolutionary models of time discounting. Okay? That is also interesting. But maybe not so much, or not enough to spend another 20 minutes and then losing the phylogenetic stuff. Okay, so these models, so let me just give you a few words about the time discounting. So how do they work? These are very special models, in fact. So the idea here is the models are, the environment is such that people always make kids at one specific age, at a fixed age. Okay, let's say tau. And then, and they have some number of kids, x. There's a relationship between tau and x, and what evolution does is selects the relationship between tau and x. Okay, so the curvature of the utility function, and the tau, which is the exponential thing. Okay, so there's a way to determine this. It's kind of very neat. Okay, and it gives you exponential discounting, hyperbolic discounting at times, and things of this sort. Okay, so check it in Robson and Samuelson. Okay, but the logic is the same, exactly the same. In that case, there is no randomness; it's a deterministic model. But again, it's you're looking at the growth rate of the fitness mechanism, and you compare growth rates. Okay, there are many other models which do many other evolutionary models. Again, let me say this a couple of minutes. So, what are these? Okay, so we've seen an evolutionary model for risk. We've seen one for, we haven't seen, but I'm telling you there is one for time preferences. Okay? Then there are others which are kind of interesting. There is, so I'm thinking about the ones that people have written up, and I want to argue that they look like what we're looking for. They are looking for these are all models where evolution selects some relatively general feature. Okay, so another one is about what enters into the utility function. In a trivial model, fitness enters the utility function. But suppose you can't quite do fitness, and then there's the evolution plays with what you evaluate in the utility function, and this gives you state-dependent or choice set dependent utility functions, which are things that more or less we observe. So this is kind of interesting too. Okay, there are other models, one of which I also have written down, where what happens is you try and see if evolution selects, again, it looks a little bit like this, where there is a cost. If evolution selects a decision architecture, so think of these models where there are multiple selves. Okay, so these models with multiple selves are behavioral models where there's a self which does a bunch of things, and there's a self which does a bunch of other things, and they interact, and sometimes one wins, sometimes the other wins. So these are models where the architecture are hierarchically structured, typically, right? So there's a main self, and then there's these other guys, and the main self decides who wins. So you can compare this with another model where there's just a unique self which is all integrated and does the best possible. So these are, you can find conditions under which when the first model, the second model, the one with all the selves, is too costly in terms of energy, so there is a cost of going there, then in those, you can find conditions under which the dual self model works, or the multiple selves model actually is selected. Okay, so what I want to say is a lot of this literature is about finding out conditions under which relatively behavioral structures can be supported by an evolutionary model. It doesn't have to be what this literature is about, but it's often what this literature is about. Okay, so you can check it out. The logic, though, it's always the same. Okay, the logic is you look at geometric means, you compute them, and you compare them. Is this kind of clear? Okay, I really have half an hour. So let me say something else about evolution. Again, let me have only 5 minutes. Sorry, I'm speeding up, but so a big debate since early on is, can we have group selection? When do we have group selection? Can we think about models where things are selected by group selection? Typically, social preferences or things of this sort are thought of as selected by group selection. The logic, of course, being that in a prisoner dilemma, if your type is a cooperator, you're invaded by a non-cooperator and you die. Okay, so it's very hard to think in that simple basic model. Of course, cooperation is good at the group level, but at the individual level it's not, right? So when you really write down these models carefully, evolutionary models carefully, at the end you're gonna end to the Nash equilibrium, to some selection over the Nash equilibrium, or if there's more than one, and this non-equilibria like cooperate in the prisoner dilemma are never going to be selected. So, but people observe them, and so people have said, well, it could be group selection. Okay, so there is an issue, there is an important issue, which is about when does group selection make sense? Does group selection make any sense? Okay, so the standard rough. So the standard model or the standard example of an environment where group selection can work, it's called the haystack model. It's been written by John Maynard Smith, biologist, and the objective of his writing down this model was to show that it doesn't really work. I mean, that it works, but the set of assumptions that are required for group selection to work are very strong. Okay? So let me give you an idea of what this is, and you'll understand. So the idea is the following. Suppose you have a lot of populations, the haystacks. Each one is populated by 2 mice. Okay? So there's a lot of haystacks. Each one has got 2 mice. These 2 mice are drawn from the population. They're either cooperating or deviating. They're playing a prisoner dilemma. Okay? So simple strategy. One is playing C all the time. The other is playing D all the time. Okay? So what's the story here? The story is the following. So the environment is the following. The haystacks are separated. There's 2 mice in every one at the beginning, and then, of course, they reproduce. But there's 2 mice in the beginning. And the reproduction, of course, is the payoff in the prisoner dilemma. So in the haystack where they both C, they grow fast because they're both C and they do whatever, the prisoner dilemma CC. Okay? In a haystack where there's a cooperator and a defector, when the defector wins at the first turn, but then the cooperator dies, for instance, we suppose it's 0, the cooperator dies, and so, okay. So that's the story, right? So what happens here? So the story is, suppose that this haystack stays separated for a number of periods. And then, let's say T periods. After T periods, we reshuffle everything. All the mice are put in the center, then we reshuffle and we send them 2 by 2 in the haystacks. Okay? That's the logic. Okay? In this world, it could be that C is selected, that the group selection works. Why? If T is very long, there's going to be a lot of cooperating people after a while because they do very well. The crucial point is that they are never invaded by anybody else for T periods. Then after T periods, you reshuffle, but for T periods, they're not. So if you let them grow fast enough for these T periods, then you reshuffle, then of course, this takes the proportions down because then they are in some sense invaded. But you can construct this again, computing geometric averages, you construct it so that, in fact, CC wins. Okay? So that's the story. Now, there are many assumptions implicit here. The crucial one is that there is no invasion, really. Okay? So there are these populations which are separated for a long time. They don't connect. Okay? So I don't know, whatever you might think this is a good assumption, in which environment or in which situation you might think this is a good assumption or it's not, but that's the story. Okay? It's very hard to think of this. This is the John Maynard Smith point. I think it's very hard to think of this as a model of social preferences because that would have to mean that this is what the population was for that was the right environment for the whatever thousand millions of years of hunter and gatherers. Okay? So, and you might not buy that, but is this clear? So I just wanted to have it up. Because it's an important point. There's a whole group of economists who are thinking along this direction. Bowles, Gintis, and okay. So they're thinking about this direction. They're writing down models of group selection, and they're thinking, this is relevant. So, so we should have it. Questions? Otherwise, I go to the phylogenetic stuff. I mixed up everything. Yes.
So in this group selection, it's rarely observed that types differ, right?
Say again?
It's rarely the case that types differ. So I guess what I'm trying to ask is, we started off on 2 premises, right? There's some kind of bundling, so there's distinct groups, say, which is somewhat similar to the idea of group selection, as of today. The other is heterogeneity.
Yeah.
I recently came across some work by biologists, but I can't really summarize it well. The idea was it could be optimal for stocks of birds to have different risk preferences. Let's call it risk preference or risk type, risk-seeking behaviors.
Yeah.
And the intuition was a bit, you need this alarm bird, right, who makes a lot of alarm if there's a fox coming, but overly, if you do too much alarm, that can never be efficient either, because then, you lose too many calories, because even if it's only a rabbit, the whole stock. So they were arguing, and it seems there's some evidence also that there's an optimal diversity in preferences for a group, right?
So this was group selection argument, or was just a basic evolution?
This was more or less just, could it be that at a group level diversity is good? Again, that would, as always in evolution, depend on the environment. But do you know of any models that would look into groups or group selection favoring some optimal level of diversity, which would match very well into what we observe, right? Because society is also very much by the level of diversity. It's not that one country is risk averse, the other is not. They're also very much by the variance of these preferences.
So let me say, then Stephen raised his hand, maybe he has an answer, but let me say one thing first. Yeah, I think that's a very good point, and it's something, so, in the following sense. These models, not just the group selection, even the standard evolutionary models, these are models where somehow I was asking myself, I'm asking the question aloud, I don't know the answer. So these are models where, there's always one type which wins in the end. So there is no reason why it should be. You can have a distribution winning, right? So that's perfectly fine, because the evolution looks at the whole, even, not just group selection, even in standard selection, in the same way as the utility function, the fitness function changes if you have aggregate versus idiosyncratic stories. The evolutionary story considers the whole environment. So it could very well be that, you win okay. So I don't know of any model which does this. I don't know historically why, it's modeling is so. People have not looked for that. And the following says, so in the model, both in the models that I work with in cultural transmission and the model of phylogenetic splitting, the whole point is exactly to produce heterogeneity, right? So the models I was working on in cultural transmission, the whole point was exactly that the biology model were generating a unique homogeneous cultural trait in the limit. And I wanted to construct models where in the limit you had a distribution of traits, a proportion of both traits, right? So that's exactly the way we thought about cultural models, but somehow in evolutionary models, this is not the case. And when you look at risk preference, they give you, now, again, if you're thinking of that as principal and parameters, then maybe it has some sense, as we were saying in Chomsky too. There's a one unique universal grammar. There's one unique general utility function. And then the parameters change. So if that's the story, we can do that. But why people haven't looked in evolutionary models to stationary distribution over traits, that I don't know if anybody's done it, I don't know. Stephen.
Well, it's a related question, and that had to do with...
I was hoping it was an answer, by the way.
Well, it's related to that, which is consider a population that had three types: cooperators, defectors, and the punishers. In
Yeah.
other words, there's another type which has the feature that when they run into a defector, they kill them.
Yeah.
And so there you can get an equilibrium in which the cooperators and the defectors somehow coexist. But so that was comment number one.
No, if it's costly to defect, in the end when there are no defectors, if it's costly to punish, in the end when there are no defectors.
Oh, so the trick is that the cooperators are nicer to the vigilante. So that you could think about more elaborate.
But you need to recognize them, right? You need to be able
Yes.
to identify them.
Yes, and so if you then think about what it
So you
means
need some
to have
information
the...
structure then.
Right, so that's also, as I thought,
Yes,
this was an answer.
Yeah, so I put that on the table as one possibility, is that, if we're thinking about populations of animals, there are the notions of alphas and et cetera. There is an interpretation to what that would mean in terms of the heterogeneity. My question really, the reason I mentioned that was the question about the notion in evolutionary game theory of low-cost punishment of people that deviate from norms. Is there an analogy in the evolutionary literature that you've worked with that has something like that?
I don't know. It's a good point. I don't know. I haven't encountered it, but I don't know the relationship well enough. But that's a good point. Yes, it's related. That would work. Yeah, I should check. I don't know. It might very well be. Yeah. Other questions? All right, so 20 minutes. Let me talk about phylogenetics. I told you I was going to confuse you. Please tell me you are. We've seen all sorts of stuff, okay? So this is a complete different word. These phylogenetic models, completely different setup, different word. Again, this is all related, but the relationship has to be worked out by somebody has to work out this relationship. I can only say that, you know, there is one at some abstract level. Okay, so what are these models? So these are essentially statistical models of splitting. Okay, so let me start, you know, with the standard one, and rather than tell you in general how this model works, let me tell you about this model, and you'll see how this thing works. And people have done this to everything. Okay, so here the question. This is language. Okay, as I told you before, this is two guys, by the way, Atkinson. So as far as I can understand by reading the literature, not of course being an expert, by reading it, this is the fundamental stuff. I mean, it's not the frontier in the sense that there's a lot of people who have added bells and whistles to this, but it's the fundamental of the frontier. Okay, the rest is bells and whistles. There is no really fundamental different models more sophisticated than this, as far as I understand. Okay, so I'm going to talk about this. So what do? So the problem, they are trying to ask a very simple question, which is, there is a relationship between a bunch of languages. We know there's a bunch of languages which are related. We call them Indo-European languages. We can go back and try to ask ourselves the question, at some point we have a model in mind where, you know, these different languages are the result of splitting from previous languages. So changes from previous languages. So we have in mind, essentially we have in mind a tree structure. I should do lines. Well, it's okay. So we have in mind a tree structure where, you know, we start from a language here, and then we go down and it splits, and then every single one, maybe longer time, splits again, maybe shorter time, splits again. So we have in mind a story of this form, okay? And then, yeah, let's say that this is the whole thing, right? So now what we do is we know everything about this language, these languages. These are the leaves of the trees. These are the languages that we observe now, okay? So this last period is now, okay? We know a bunch of stuff about this thing. We know how related they are to each other. And so we try to construct a tree structure. Okay? We have in mind this idea. This is the assumption of the model. The model is that the world works by separation of trees. Okay? Like that, by splitting. It's a tree structure splitting. Okay? So the world is like this. We know this. Maybe we know something about one of these languages, and we are trying to construct what's happening. Okay? And in the mind or in the problem of these two guys, the idea here is. When, well, let's say that, yeah, so there are a bunch, so, okay, so when is this node? Okay, which is the original language from which all the others split, okay? Where all the other, I mean all other Indo-European languages, okay? So in this story, what we're looking for the Proto-Indo-European. So the first Indo-European language, we put as least all the Indo-European languages, what we think are the Indo-European languages. So there's a lot of structure that we add. We think we know what are Indo-European languages, and then from that basis, we construct the Proto-European. Now, we're not after constructing the language. What we are after is constructing the time at which the first split happened. Okay, so we're trying to estimate here. We write down this model. The model is a stochastic process, as you can see. It's a very simple stochastic process. I'll tell you in a second what are the states of the stochastic process, what is the random variable moving over time, but this is the logic of the thing. And the crucial point is, you know, when do this split happen? Okay? And so in this particular case, these guys wanted to know how far back was the Proto-Indo-European language. And why is that important? Well, because on the basis of archaeological data, there are two theories. One is that the Indo-Europeans were this population, Kurgan, which were coming from the steppe, from Russia, Ukraine, and coming down. And this coming down to Europe and then and to India on the other side, this happened about, we know, about 6,500 years ago. And so that would be, so if they are the original Indo-European, if they spoke the original Indo-European language, then the splitting happened 6,500 years ago. If instead the original Indo-European language speakers were the people living in Anatolia, which started bringing agriculture around Europe and India and the rest of the world, if these are the original Indo-European languages, then these guys started going around the world 9,500 years ago. Okay? So the whole idea here, which is kind of interesting, I think per se, the whole idea here is that, you know, we write down a stochastic process, we estimate the parameters of the stochastic process, we run it back, and we see when this point where the first split is, and then without any, in principle, without any archaeological data, we are saying, you know, okay, the split was 9,500 years ago, bang, that it means that the Anatolia guys are right, okay? That's actually what they find. Okay, that the Anatolia guys were right, that the split, of course they have a probability distribution, the model gives you a probability distribution over the split, over splitting times, over the original split, and you know, they show that this probability distribution is concentrated enough around 9,500 years ago to exclude with the 97% probability the Kurgan. Okay, so that's the logic. So how do you construct these models? Okay, is this clear? Is the question clear? Okay, so, and what is the state space? The crucial thing is what the state space here. So the state space typically in these models are what linguists call cognates. Rather than defining it, let me give you an example. Okay? So take a bunch of languages. English, German, French, Italian, Greek, and Hittite. I learned that this is the right way. Okay? And look at a bunch of words. So what we do here, this is a little bit like, you know, like Armin was saying today about, I think he was saying, at least he wrote in the paper, when you look at genetic models of you know, genetic diversity, genetic distance, you look at loci, again, what do you say in English? I don't know. In Italian, if you say loci, you look at locuses which are really neutral, okay, which are not typically selected. This is kind of the same way. So what you want to do is you want to do a basic words that are, you know, repeated all the time in a language. They're very clear, common, that they're not borrowed from one language to another, right? So if somebody invents a technology, most probably in the other language, that technology is called with the same name. But here the question is mother, father, water, this kind of words, right? That, you know, you use all the time, and if you have a word for water, then, you know, it's probably going to stay unless, you know, your language changes completely, okay? So let's look at water, okay? So it's water here, it's Wasser, it's O, it's acqua in Italian, it's nero in Greek, and it's vatar. Interesting. Now, I don't know how they pronounce it. I don't think anybody knows, but in Hittite, it's vatar. Okay? So then look at this, and you essentially look at similarities. You can do this carefully. If you're a linguist, if you're me, you're saying these three are the same cognate. Okay? So cognates are similar manifestations of a concept, of a linguistic concept. Okay? So linguistic manifestation of the concept. So these three are the same. O and aqua are the same. This is the second cognate. And this stands by itself. Okay? So now, in one word, we have three cognates. Okay? Compute 200 words. These are called Swadesh lists. So there are 200 words for a bunch that are selected to be nice in this sense for a bunch of languages. Okay? In this case are 70-something languages, 200 words each language, and these 200 words have a bunch of cognates between them. Okay? So now the stochastic process of the tree is on cognates. Okay? So that's the logic here. So you want to say, so what you're looking at is, you know, there was the Hittite were calling water Vatar, and, you know, we kept going here, English and German. Okay? They kept going. And at some point, the Greek went to Nero. That's a switch. That's a new tree. That's a new branch of the tree. Okay? As long as you stay along the cognate, there is no changing. Okay? But when you go to Nero, you jumped away. That's the story. Okay? And of course, there's a lot of this. There's thousands of these cognates in this list in the end. And so each language, in some sense, it's a vector of cognates. Okay? So, you know, Italian is 2 for water, is the 17th cognate for mum, and so on, right? So Italian is a list of things. So the way you construct this process now, stochastically, what you do is you look at a list of cognates, and so what you need to do is you need to identify probabilistically what was the list of cognates that the Proto-Hittite, by identifying, I mean, you estimate this, right? So the way you have this process is, okay, so this is the original Indo-European, then we moved, and then we moved here, and then we moved here, and then here, okay? And this kept going down. Well, this would be that there's somebody still speaking the Indo-European, maybe they do, okay? The Proto-Indo-European. So the idea here, each branch separation is a change in one of this, in this configuration of cognates. You see what I mean? And what you're doing is you have the final data, right? So you have a list of all these things. What you're doing is you're estimating what your estimating procedure does is it estimating the topology of the tree. So we assume it's a tree. We are looking at, you know, likelihood of the data over all possible trees. Okay, and of course this is computationally complicated, and there are all tricks to do that. But you're trying every tree, and so what you're selecting is the initial list of cognates. You're selecting the rate at which split happen. Okay, so it's a stochastic process. So the idea here is every cognate splits, every list of cognates. So every cognate changes with some probability. So at some point you have a change in the cognate, and how often that happens depends on the, you know, on the speed at which the stochastic process changes. Okay, so that's one thing you need to estimate. Okay, so you estimate the initial values, you estimate the rate at which things change. Let me go back to that in a second, but the rate at which things change, and the structure, the topology of the tree. Okay? Which data do you have? Well, you have the data about the final objects, the final leaves here, and a bunch in the middle, various constraints. For instance, you know that French, Italian, and Spanish are coming from Latin. Okay? And you kind of know when they separated, because, you know, it has to have happened before or right after the invasions, more or less at the time of the barbaric invasion. Huh? We like to call the Germans barbarians. So, right, so before the barbarians came, we spoke a beautiful language, and then, you know, we split in 3 beautiful languages. So, but we know when that happened, okay? So that's a constraint. You know something about what that happened, and you know when it happened, and how it, and which language was this, and which language was this, right? So you have a bunch of constraints or data along the tree, and you're using this, of course, to compute, to estimate the rate of change, the rate at which these cognates change. Now, typically these models had a unique rate of change, which, I mean, it's, it's very restrictive. So every possible, the switch from water to Nero, you know, happens at some probability over time, some Poisson arrival. And it's the same as the switch from mother to whatever it's called. Mother is called in Greek, okay? So if you assume that the rate at which you have the switch is constant over the tree, of course you only have one parameter. Typically what these guys do is they assume that this rate is different for every cognate, so they allow cognates to change at a different rate, but they assume that these different rates are distributed like a gamma, so there's only one parameter there. And the states and one parameter, and then they assume some kind of possibility of speeding up or slowing down of the process, but that also is very restricted, okay? So it's a special process with a bunch of relatively small number of parameters, okay? So that's the story, yes.
So do I understand correctly, you get a distribution of trees?
Yes, I'll show you this.
And then you take the most likely one, so to say?
No, you look at the distribution and you...
Because it's not easy. I mean, there are so many possible trees, probably.
Right.
And then it's unclear how much weight to put on, you know, various differences. For example, maybe you care more for the first tree rather than, you know, later trees, or you put equal weight on each separate. Yeah. You know, there's so many ways to evaluate what is the most.
Yes. So one of the things they do, these guys do, is typically they work with Bayesian models. So they, you know, they explicitly set their priors about the structure of the tree. Okay? So, of course, this is very extreme, again, in the case in which you look at Italian, French, and Spanish from Latin, but there are things where you don't, I don't know, is Latin a Latin language? It is, but suppose you don't know that, well, okay, so your prior is whatever, the explicit, the prior in that case, and they go ahead. So that's one of the things they do. But one of the big things is exactly the following. I mean, it's exactly the fact that they are showing, so originally what they were doing is they were maximizing likelihood and coming up with one tree. Now, this is okay if you can look at all the trees. There are too many trees here, so you can't quite do it. So typically what they do is they have a mechanism to sample trees, and they give you probabilities over of these trees that they sample. Okay? I'll show you how they. We'll have to stop watching Beethoven here. Okay, so the final, for instance, in this paper, as I said, the problem is so compute all the rates, the rate of change of various cognates, go backwards, and try and estimate or try and see for every tree, you know, when is that Proto-Indo-European split, right? So what you come up with, though, because you have all these possible trees, you're going to all these trees and the various probabilities, you're looking at a probability distribution over the trees, and in particular over the time at which the first tree, so over the trees, the time at which the first split happens. Okay, so so they give you things like this, right? So this is age in millennia. You see over the trees that they sample, the station distribution of trees, the trees that they sampled, you might not see this is an 8, this is a 10. So the mode is 9.5, and the distribution is centered enough so that the 6, 5.56, which is the Kurgan, which is what they want to exclude, is right here. It's very much the tail of the distribution. So they say, look, we found out that it's the Anatolia. You see what I mean? So that's the logic of these things. The other way in which they present results is this. This is called a consensus tree. It's not a consensus network. It's not a tree. What you do is look at every possible split. Suppose you're asking the question, is there a split between these two strange languages? They don't exist, right? So did the Indo-European split into two at the beginning, whatever, two different things where one cognate changes or didn't change, right? You ask that question. The question is look at over all possible trees and look at the probability that every particular split had happened, right? And encode it. So then, of course, this is not a tree anymore because you're looking at all possible splits over all possible trees. The result is not a tree, it's a network, right? But what they do is they give you, for instance, now you don't see, but they give you the probability distribution of this split, right? In 41% of the trees, we have this split. In the other ones, we don't. You see what I'm trying to say? So the way they report data, it's always probabilistic. And when they are able, this is a little bit more tricky how they do, but this is the final tree. So this is the consensus tree. So it's the one they, in some sense, is the one they choose as maximizing the likelihood, which is some sort of a median overall possible. And it's a little complicated the way they compute it. It's not really the one which maximizes, but you see that every split has got a probability. Okay, so that's the way. So this is also, in some sense, it's a way of representing a distribution over trees. You see what I mean? And also, the length of this thing is the length of time. It's proportional. It's written proportionally to the length of time. You see what I'm trying to say? So this model is very. So I have 1 minute. Let me finish. So you understand these models are, on one dimension, very sophisticated. Typically, in terms of the very sophisticated enough in terms of the statistics behind it. And the computation behind it. In some other dimension, the model is completely trivial. There's an enormous amount of improvement that you can think about, right? So think about this, the way this goes. There is no contextual information about the splits, okay? So in some cases, like in this case, you might not have it, it's okay. But in many situations which we, for instance, in ethnic trees that, that we have a lot of information because of history. So having cognates about languages, even though you know that some language existed, still you don't have the cognates. Ethnic characters are easier to come across in history. So you can do these things with history, with the ethnic traits and all things of this sort, but then the model is very ad hoc. An economist would never write down a model like that, a stochastic process with a fixed rate of change, okay? That rate of change has got to depend on all sorts of stuff. It's useful to think about what does it depend on, okay? So it's not enough to say, there's a gamma distribution. I would like and want to, when I think about ethnic change, I would like to model ethnic change, not just as a Poisson arrival process with a constant probability over all ethnic groups. You see what I'm trying to say? So there's all sorts of contextual information that you can add to this thing and come up with interesting models. By the way, as I said, these people, so this is one of genetic, so Cavalli Sforza has done one of these for genetic sort of ethnic groups based on genes. This is one on religious. It looks upside down because I couldn't put it. But this is religious splits. Okay, so the point I want to make is that you can do this. The people have done these things on everything. It's a technology, actually. There is a software out there which computes it for you. It's easy to do, and people have done all sorts of stuff. The point I want to make is that this is from our point of view, it's a very ad hoc, relatively trivial model. And it's worthwhile to think about these things to narrow down the question. Maybe you want to understand a few splits in a relatively shorter horizon, but you want to get into and understand them more carefully. Okay, so that's the stuff I want to do. I'm done, and I'm also tired. And the cultural transmission stuff, who cares? Okay, apart from me and Thierry, nobody else. Questions? I'm not the only one tired. Thank you.